We are starting this lesson in your foldable. You'll want to make sure you have it and find the tab related to rectangles. The cover here, definition of rectangles. Let's get it started. First and most important probably is to realize right off the bat that a rectangle is a parallelogram. The definition is that it's a parallelogram. That means that it has all those properties for parallelograms that we saw in the past couple of lessons. I do not want to write them all down again. Let's take advantage of this foldable. Let's say that it's a parallelogram, and therefore you can point up to all that stuff that's right above it in the parallelogram categories. I'm not going to list them all. We're just going to remember. But what makes it special? What's so special about this parallelogram that makes it a rectangle? Well, it's a parallelogram with a right angle in it. And you probably already know that. Every rectangle has right angle. So you're going to always see a right angle or 90-degree marking there. Now, let's just apply what we know about parallelograms. Since it has a right angle in it, just like all parallelograms, its opposite angle is going to match. So there'd be a second right angle here. And just like all parallelograms, its consecutive angles are going to be supplementary. So what do we get with 90? 90 plus what makes a 180 total? Of course, that's 90 again. So of course, it's going to have 4 right angles. So let's just change this to make it a little bit more interesting. It's got 4 right angles. A parallelogram with 4 right angles. Well, it turns out those right angles make some other stuff happen. And so if you'll flip to the special properties on the back side of your rectangles flap, the special properties of rectangles, there's one important one that you want to know. And it is this. Write this down. Its diagonals are congruent. So you're going to want to also draw this. And let's use our technology. I'll use some real straight lines. If we were to take this diagonal of the rectangle measured out, it would be congruent to the other diagonal measured out this way. So we already know they bisect each other, but turns out now, not only do they bisect each other, they're the same length altogether. So tick marks here and here are going to be exactly the same tick marks here and here, all 4 of those little parts. And let's put some letters on this to name some things. Let's just call this A and around B, C, D. We're saying that A to C is equal to, on this direction, is equal to B to D on the other diagonal. And some examples are going to apply that. So now we're in your whisk packet with these examples. Given rectangle QRST with QP is 4 and RS is 6. I want to add that to my picture. I find QP right here on that diagonal, 4, and RS, that's the side of my rectangle, that's 6. And so we're going to find some measurements. First, PS. P to S, that goes right here. Well, we already know that this is a parallelogram, so if I have 4 on this piece, I've got 4 on the other part of that diagonal. So PS is going to be 4 for sure. How about RT? Now RT, that goes all the way across the rectangle. We just learned about diagonals of a rectangle being congruent. So RT is going to be congruent to QS, the same both directions. So how far from Q to S? 4 and 4 is 8. RT is 8. And then our last one is ST. What is this distance right here, ST? I'm going to just call it X. How can I figure out that distance? This is going to go back to the famous theorem that seems to pop up in all of these problems, the Pythagorean Theorem. We're going to note that this is a right angle. And it being a right angle gives me a right triangle if I look for the right one. I'm going to highlight a right triangle. So we've got this distance, this diagonal, this side, and this side. And I think it'll be helpful if we were to draw that out just off to the side here. So let's do it. Okay, so I've got a little right triangle, half of my rectangle, right angle. What parts do we know? Well, we know that this is 6 here on the side, and if you remember R to T, that was our distance on the diagonal, and that we came up with as 8. So our question, this is going to go back to the Pythagorean Theorem, which is the A squared plus B squared equals C squared equation. Now, hypotenuse is across from the right angle, that goes in as my C value. So with 8 in the C spot, we'll put x squared and 6 squared in the other 2 locations. And let's solve it. I'm going to square these out, so I get x squared plus 6 squared is 36, and 8 squared gives me 64. Let's subtract off that 36 from one side, do it to the other side. I'm not drawing my line, you guys like that line. Then I've got x squared all by itself here, and the difference between 36 and 64 is 28. So x by itself is going to be the square root of 28, which if we're going to grab a calculator and take the decimal for that, the square root of 28 comes out to be, I'm getting about 5.3 if we're rounding, so 5.3. And that's the distance for s to t, it's about 5.3. All right, so right angles, usually you get a little right triangle and Pythagorean theorem. Be on the lookout for those. Let's look at this example. Now this is the same picture, but we're going to clear it off because we're going to find some angle measures. Angle 1 is 33 degrees. I'd like to add that into the picture. Let's put 33 right in here and find the measures. Now we know it's a rectangle, so I think it's important that we mark a right angle. All these are right angles, and that gives me a chance to find my first one. What's the other piece of the right angle? If angle 1 is 33, how much is left over for angle 2? So angle 2 is going to be 90 minus the 33 portion of it. How much is left over? 57 degrees for angle 2. Okay, now angle 3, right inside here, this looks like it's an obtuse angle from the picture if it's drawn to scale. How can I get angle 3? Well, it's a vertical angle with this angle down here. That doesn't help me a lot. I'm going to have to go and think a little bit and remember that these diagonals are congruent. You might be like, well, what does that have to do with these angles? Well, let's mark them and we'll check it out. These diagonals are congruent. Okay, now I want you to look at the triangles that are there. And I'm going to highlight this triangle right here, triangle TPS. What do we know about that triangle? Well, look at it, guys. These angles, or excuse me, these sides are congruent. What kind of a triangle is that? It's got 2 equal sides? Isosceles. So back to our old theorem for isosceles triangles. Remember, if 2 sides are the same, these angles across from are the same. So wouldn't we be able to put 33 degrees in here? Yes, we can. And once we know these are both 33, we got just how much left over for angle P, which just happens to also be this angle 3 angle. So let's just add up what we have. 33 and 33 make a combined total of 66. And if we take the 66 away from a 180 in a triangle, we've got our missing angle, 114 degrees. So we have 114 degrees here. It's also the vertical angle here. Look at all those theorems coming back to haunt us. 114. All right, I hope you got that. If you did, then angle 4 should be a piece of cake. Angle 4 just goes back to these old linear pairs we've seen a million times. There's 180 degrees right there together. So for angle 4, I'm thinking I'm just going to take 180 and subtract away the 114 on that side. And lo and behold, I get 66. Okay, so be on the hunt. Those rectangles having those diagonals congruent means there is also 4 isosceles triangles in there. I'm excited to do this next one. Angles again. Angle DAC is 2x plus 4. Let's find angle DAC in the picture. Angle D. A is where the bend happens and down through C. So right here is our 2x plus 4. And angle BAC. Angle BAC goes from B, makes its bend at A also, and comes out through C. That's this part. This part right here is 3x plus 1. Now, I'm not going to say that those are congruent, but I do know it's a rectangle, so this is a right angle. So these guys might not be the same size, but I know for sure that they make 90 degrees. They're complementary. So that's the way I'm going to set up this equation. I'm going to add them together, get a combined total for them. 2x plus 4 on that first angle, going to combine with 3x plus 1, and 90 degrees is the total. Combining like terms, 5x plus 5 more makes 90. And taking away that 5, I'm going to get 5x, brings this down to take away 5, 85. And let's divide that by 5. 5 goes into 85 17 times. So the value of x is 17. We are looking for the measure of angle BAC. So BAC, that's this angle right here. Let's plug it in. We're going to go 3 times 17 and then add 1 to that. So 3 times 17, what is that? 51. And add 1 to that. Grand total for our final answer is 52 degrees. Okay, now this happens a lot. You'll get a description like you see here, but no picture. So your job is to be smart about it. Just draw a picture. In rectangle GALS, and then let's get these measures. Let's draw the rectangle first of all. So draw yourself a rectangle. And this is important. I don't know if we've ever talked about this. If we haven't, it's been a long time if we have. You name the rectangle GALS by starting at any vertex and then going around in order. So if I start here, for example, at G, I might work my way around. Let's go to A and coming around L and S. You don't want to jump around. You want to go in order. You can go backwards around if you want to, but don't be skipping around. So there's my rectangle, and GL is, GL's a diagonal. GL, this diagonal, is 3A plus 6. And then AS is this diagonal. Ooh, this will be fun. And that diagonal is 5A plus 18. I'm not sure how to write that. Let me just kind of put it out here. 5A minus 18. Find the length of those diagonals. Our theorem to the rescue, the diagonals theorem. Rectangle diagonals are congruent. So that means that GL and AS are equal. Let's just set them equal. 3A plus 6 is equal to 5A minus 18. You can solve this. Maybe pause the video and do it and then see if you got the same thing I did. I'll work my way through it.
There's many shapes, rectangle, many shapes as quadrilateral. Rectangle's one of them, the corner square. For right angles around, right arm, left arm, right leg. Quadrilateral, we do the quadrilateral dance. Let's do the quadrilateral, we do the quadrilateral dance. Yeah, come on.
Okay, if you're back with me, you got A is 12. If you didn't get that, check out the work here, fix any errors you might have made, or let me know if I made one. I got A as 12, so the length of the diagonals. Let's start with our GL diagonal. So GL is 3 times the 12 plus 6. We're just plugging it in. 3 times 12 is 36. 6 more makes 42. And AS is my second diagonal. Sure hope I get the same answer. They should be equal. 5 times 12 minus 18. 5 times 12 is 60. Take 18 away from 60 and you get 42. They check. I love it when life happens like that. Everything works out just great. Of course, you got to try your own. See if you understand by giving the try these a try.